Hello everybody, and welcome to page 142 of the workbook. We're going to be working through exercise 3 together. This is a long problem with a lot of information in it, so before we do anything, let's just read the problem from start to finish, and then we'll go back and see if we can make sense out of the information that it's giving us. Okay, so the magnetic field B around a long, straight, thin wire carrying a constant electrical current I satisfies Amperes Law, which states that the line integral of C of B dot dr equals K times I, the electrical current, where K is a constant and C is a closed curve surrounding the wire. Okay, and second sentence experiments show that this magnetic field B is tangent to every circle perpendicular to the wire and has a center on the wire. Okay, well that's a lot of information, so let's go over to the picture and see if we can make sense out of some of it. All right, so notice where the wire is. Okay, we're kind of looking at the wire head on, so you have to sort of picture the wire as coming straight out of the page at you and going straight back into the page. That's the wire that's carrying the electrical current that they're talking about. And then you can see the curve C that surrounds the wire. That was the C that was involved in the line integral. And then finally, the magnetic field that's generated by the wire is circulating the wire. Okay, that's what you're seeing here. All right, and so Amperes law is about what happens when you take a line integral through that magnetic field that's generated by this wire. Okay, it basically just says that if you take that line integral, you're always going to get a constant multiple of the current, K times I. Okay, and it's our goal in this problem to basically derive a formula for this magnetic field and to show that it has an interesting property. Its divergence is 0. It's a divergence-free vector field, as it turns out. Okay, so we're going to do this in stages, starting with part A here. Okay, they ask us to use Amperes law to show that this magnetic field magnitude always has a formula given by K times I over 2 pi r. Okay, you can see kind of some components in that formula. I is the electrical current and r is the radius of the circle. So the bigger r is, the smaller the magnitude of our magnetic field is. Kind of makes sense. It seems logical that our magnetic field should be weaker if we're farther away from the wire. Okay, so let's see if we can do that. So we'll start with Amperes law, okay, up here, which says that K times the electrical current is equal to this line integral. Okay, we'll just see where that leads us. All right, first thing that we're going to do is to go back to a formula relating to the dot product from way early in the course. So B dot dr, you might remember that U dot V can be rewritten as the magnitude of U times the magnitude of V times the cosine of the angle between those. We're going to use that fact. And then I'd like to ask the question, what is the angle between the vectors B and dr? Let's go back to our picture for a minute here. Okay, so B, the magnetic field vectors B, are the vectors that you're seeing here. Okay, so imagine that you were standing right up at the top of this circle. Dr is just a vector that's also tangent to the circle. It's like a displacement vector saying if you were an ant on this circle and you wanted to walk counterclockwise around it, the first step that you would take would move you exactly in the direction that the magnetic field goes. So the observation is that the B and the dr that we see here are actually parallel, which means that this angle between them has to be 0 degrees. Okay, since B and our displacement vector dr are parallel. Okay, so that's a useful observation because the cosine of 0 is 1. So really then, what we're taking is just the integral of B times dr, and we're going to make one assumption, physical assumption about this vector field, and that is that because we're on a circle that's equidistant from the wire, we're going to assume that the magnitude of the magnetic field is constant along that wire, or I'm sorry, along that curve, which means that we can pull that B outside of this integral. Okay. since we're making the assumption that the magnitude of B is constant along our circle. All right, well, if that's true, notice that all that's left here, all that we're adding up, is lengths of dr. So ask yourself, if you were to integrate along this entire circle that we have up here, let's get rid of some of the markings that we had. Okay, so if you went around this entire circle and just added up the length of the path that you're walking along, what would you get? Well, you would have to get the length of the entire circle, and we know how to find the length of a circle. We can just take its circumference. Okay, so length of C, and then using the formula for the circumference of a circle, that's just going to be 2 pi r. Okay, so notice where we started and where we stopped here. We had k times I, that's equal to the magnitude of B times 2 pi r. We can take that equation and solve it for the magnitude of B. Just divide both sides of that equation by 2 pi r. And notice we get exactly what we wanted to show. Okay, that was this formula up here. So that's part A. We have a formula now for the magnitude of this magnetic field as a function of how strong the electrical current is and how far away we are from the wire. Okay, so let's take a look at our next task here then. So part B, so they start us off by giving us a vector field of unit vectors that you've seen a few times before in this course. Okay, I'm going to kind of leave it to you to maybe page back in the workbook and see if you can find a picture of this vector field, but the key observation is this. The vectors in F are unit vectors. They all have length 1, and they're exactly parallel to the vectors in our magnetic field. You can confirm this by looking back at some pictures in the workbook. Okay, so it's going to look very much like the vector fields up here in the picture, just that every vector is going to have length 1. Okay, so here's what we can do if we want to find a quick formula for the vector field B. We make the observation that F almost works because those vectors point in the same direction of B. We just need to adjust the length so that it matches the length of B. But in part A, we calculated the length of B. That was this formula right here that I'm circling again. So all we should need to do is to take F and multiply it by the length from part A, and we should have a formula for the vector field F. Okay, in other words, B has to look like the magnitude that we calculated in part A times F. Okay, let's take that and work with it a little bit. Do a little bit of algebra on that. Okay, so R, this R that you see down here is just the radius of a circle. You might remember that the equation of a circle of radius R looks like this, centered at the origin. So if you take that equation and solve it for R, just take the square root of both sides, we can rewrite this as ki over 2 pi times the square root of x squared plus y squared. Okay, and then F, let's write out this big ugly formula here. We can do a little simplifying here. In particular, let's take the square root of x squared plus y squared that appears in both of the terms, factor that out of these parentheses and put it together with the square root of x squared plus y squared that's there. If you do that, put those two square roots together, you're going to get ki over 2 pi times x squared plus y squared. Okay, and then we've pulled the square roots out, so inside the parentheses we've just got negative yi plus xj. Okay, there's a formula that should represent our magnetic field. Okay, that should match the picture that we had at the top of the page. Okay, and finally we are ready to demonstrate what we mentioned at the beginning of this. We'd like to show that this is a divergence-free vector field, this magnetic field. So we're going to show that the divergence of B is 0. All right, so there we just need to remind ourselves what the definition of divergence is. It amounts to taking the partial derivatives of our two components and adding them together. Okay, so if we write that all out, okay, we're going to get partial x of, okay, let's see, the I component of our vector field looks like negative kiy over 2 pi x squared plus y squared. Okay, plus the derivative with respect to y of our j component. And again, I'm just looking at the formula up here. Kix over 2 pi times x squared plus y squared. Okay, and we need to do some algebra here, so just to make it a little easier on ourselves, notice that there's a constant that's common to both of these terms that we can pull out. Okay, so you see how there's this ki over 2 pi, that appears in both of these components. So what I'm going to do is just pull that out of both of these two coordinates. And then worry about just the derivative of what's left over. Okay, so in the case of the first one, we've got a minus sign and we've got y over x squared plus y squared. If we use the quotient rule on that, just write out what that would look like. We're going to get, let's see, the low times the derivative of the top. That would just be with respect to x. If you take the derivative of minus y with respect to x, you're going to get 0. Okay, minus high d low, derivative of the denominator with respect to x is 2x over the denominator squared. Okay, the space is getting a little bit tight here. Okay, oh, and I don't want to close that parenthesis yet. Still got a little bit more work to do. Okay, do the same calculation over here, quotient rule. We'll do it a little bit faster. So x squared plus y squared, derivative of the top with respect to y, derivative of x with respect to y is 0, minus high d low with respect to y this time. Okay, there's what we get. And notice something really interesting happens here. So these two terms are going to go to 0. And if you look at what's left over, these are exactly the opposite signs of each other. So we get ki over 2 pi 2xy over x squared plus y squared squared. And then over here, minus 2xy over x squared plus y squared squared. And look what happens. These two things subtract to 0, and sure enough, we have just shown that the divergence of this vector field is 0. Okay, and that's an observation. Turns out to be very interesting physically and to also greatly simplify calculations that you might want to do with this vector field. Oh, and actually, let me correct one notation error that I made. We just calculated the divergence of B, not of F. Okay, sorry about that.